Hi everyone. Today we're going to be talking about how you can calculate energy changes from a heating and cooling curve. We are only going to be looking at water for these substances because water is very predictable. It always melts and boils at the same temperature. So for simplicity's sake, we are going to be working with that. So there's two different formulas that we'll be working with. In the event where we have temperature changes, meaning the kinetic energy is changing, so that would be the portions of a heating and cooling curve, which would be, if we were looking at it like this, that would be those diagonal portions, here, here, and here. So those would be the times we see kinetic energy increasing. In that case, you need to have a mass of your sample, a change in temperature, and then a specific heat, which is a given that you would just have to choose from. If, however, we're looking at a heating curve and you're looking at a phase change, meaning those areas in the graph that are straight and kind of parallel, that's going to be where we're calculating potential energy because there's no kinetic energy changing there. In that case, we need M and we need something called delta H. So the constants that you would use, if you're using the first equation, delta Q, M times delta T times C, these are the different values for C that you could choose from. In the other equation, delta Q is equal to H, or M times delta H. These are the different delta H's that you're using. So basically, to decide which one to use, you just have to determine what state of matter your substance is, or what phase change is occurring. So let's look at the first problem. This is going to be an example of a temperature change. So in a temperature change problem, we see that we're given the mass here, and we're given a temperature change from 22 to 75 Celsius. So what that means is if this is my heating curve, I know 0 is here and 100 is here. I'm going to be from like this segment to this segment. So this is going to be the area that I'm calculating. So my equation is Q equals M times delta T times C. My M is 25 grams. My delta T is, is my final temperature minus my initial temperature. So in this case, it's going to be 75 minus 22, which is 53. And then the C value I'm going to choose is going to be based on what state of matter this substance is in. So this is going to be a liquid. So that means I'm going to choose the C value for water, which is 1.0 cals per gram degrees Celsius. So I'm choosing this constant. So to plug it all in, I take 25 grams, multiply it by 53, and then C is 1.0. And again, I'm choosing that because my state of matter here is a liquid. So altogether, delta Q is equal to 1325 cals. In correct significant figures, 1300 cals. Okay. Another example of a temperature change problem here. We have 4 grams of ice. It's being brought from -20 to -9. So let's sketch and see what that would look like on a heating curve. Okay. I know 0 is here, 100 is here. So if I'm going from -20 to -9, it's going to be like this portion in here, okay? This teeny tiny little area from -20 to -9, okay? Haven't quite hit 0 yet. So I'm still going to be using that same equation from before, delta T, M times delta T times C. M is 4 grams, delta T, which is the final minus the initial, is going to be -9 minus -20, which equals +11. And then C, I'm going to be choosing something different here from our last problem. In our last problem, we were working with liquid water. So the specific heat I chose was one for liquid water. But now we're working with ice because this is frozen. So I want to use the specific heat 0.50 cals per gram degrees Celsius. So I'm going to plug all this in. Delta Q is equal to 4 times 11 times 0.5. This is equivalent to 22 calories. In correct sig figs, 20 cals. Okay. okay? So again, I'm just going through and I'm breaking it up and determining how many calories that would require. Third problem, very similar. We're calculating the amount of heat released. So this is going to be my hint that this is a cooling curve, okay? I have 150 grams of steam, and I'm cooling it from 122 to 100 degrees. So what I'm going to do in this case, instead of drawing a heating curve, I'm going to draw a cooling curve. So there's what we have it looking like. So we know 0 is here, 100 is here, and they're telling me I'm going from 122, which would be like here-ish, to 100, which is right there. So I'm going to be in this area of the graph. So the equation I use is Q m times delta T times C. My mass is 150 grams. My delta T is the final minus the initial, which in this case is 100 minus 122. So that's going to be negative 22 degrees. I've lost heat here. That makes sense. It's what I want to have happen. And then the C value I'm choosing is going to be the specific heat for steam, which is 0.48 cals per gram degrees Celsius. So plug it all in. Q equals 150 times negative 22 times 0.48. Delta Q is, what is it? Negative 1584 cals. Incorrect sig figs, negative 1580 cals. In this problem, we see things a little bit differently. Here, we're not given any temperature. This is our hint that this is going to be a phase change. So if we think back to our two equations, we use the temperature change one when we're on the diagonal portions of the graph, and we use the phase change one when we're on the straight portions of the graph. So what we're doing here is we are cooling things down. We're taking water and turning it into ice. That process is known as freezing. So if I think about my phase or my cooling curve here, freezing is going to be happening right about here on the graph. So that nice linear portion. So there's no temperature change here. That tells me that I'm going to use my other equation, m times delta H. So m is going to be 30 grams, and delta H for freezing, which is what I'm doing, is negative 80 cals per gram. So it's negative because it's losing heat. And again, those values are always going to be given to you. You don't have to memorize them. So you just have to plug in your numbers. 30 times negative 80 equals negative 2,400 calories. So that's how much heat is released from the system. We'll do another example very similar to the last one. It's going to be a phase change problem because, again, it's telling us that we're vaporizing and it doesn't give us any temperatures to work with. So if I'm vaporizing, that means I have a heating curve that's happening like this. And if I'm vaporizing, I'm turning from a liquid to a gas, which is going to be this section here. So delta Q equals m times delta H. My mass is 30 grams. And my delta H for vaporization is going to be 539 cals per gram. So I just have to plug that in, 30 times 539, which equals 16,170 calories. Incorrect sig figs, that would be 16,200 cals. So up until now, we've just seen situations where only one thing was happening. Either we were changing temperature or we were changing phase, but not both. That doesn't mean that doesn't happen though. In the case of this problem, this has multiple changes that are happening. Not just a phase change and not just a temperature change, but it's happening across a lot of different things. So before we kind of break through this problem, think about a heating and cooling curve. We know 0 degrees is here. We know 100 degrees is here. So in this problem, it's telling me that I have 175 grams of water. I have it at room temperature to start. So room temperature is right about here. So that's 25. Okay, I'm actually going to mark that in a different color. I think that'll make it easier. So that's 25 degrees Celsius. They tell me I'm bringing it up to the boiling point. That's 100 degrees. So I'm moving up to 100 degrees, and then I'm turning it into steam. That's vaporization here. And then I'm ending it at 115, which is going to be about here-ish. So what that means is I've now segmented this problem into 3 different portions. Portion 1, which is going from 25 degrees Celsius to 100. Portion 2, which is going from, turning it from liquid into gas, vaporization. And then portion 3, which is that temperature change from 100 up to 115. So we need to segment this into 3 different problems. So here's how you do it. Our first segment was the water changing from 25 degrees to 100 degrees. This is a temperature change. So I need to know what delta T is. So this will be my final minus my initial, which is 100 minus 25, 75. I also need to know what C value I'm going to use for that. It's going to be liquid water, so I'm going to use 1.0 cal per gram degrees Celsius. Then my water is going to be boiling, so my delta H I'm going to choose is for vaporization, which is going to be 539 cals per gram. And then my final temperature change is going to be that steam going up to 115. So 115 minus 100 is 15. So I've just kind of decided what things I needed to solve this. So in portion 1, segment 1, delta Q M times delta T times C. Again, this is a temperature change, so that's why I'm using that formula. My mass is 175.0 grams, my delta T is 75, and my C is 1.0. Altogether, that comes to 13,125 cals. Second segment then was the phase change. That's going to be the vaporization. Q equals M times delta H. 175 is my mass, that hasn't changed, and the delta H I'm choosing is the one for vaporization, 539. This equals 94,325 cals. And then the third segment is that final temperature change, the 100 degrees up to 115. So I'm going to go back to my other formula that involves temperature. My mass is still 175. My temperature change is now 15 degrees. And the specific heat I'm going to use is going to be for steam, 0.48. This adds up to 1260 cals. So my Q total, I'm going to add up this value and this value and this value, and all together these are adding up to our Q total. So we add up those values and we get 108,710 calories for this particular sample. Okay, so in this particular problem, we're going to be seeing similar to what we saw the last time, where we have a temperature change. The difference here is that our temperature change is now reducing, so we're losing heat. So I'm going to draw a cooling curve to start because I want to figure out what changes are happening. There are some hints for me in this problem. So I know I'm starting with 100 grams of steam, okay? So I know I'm going to be in that top portion of the graph, and they're telling me it condenses. This is my hint that this is going to be a phase change, and then it's cooling to 25 degrees Celsius. So I'm adding in here the knowns that I have, which is 100 degrees Celsius and the 0 degrees Celsius as my melting and boiling point. I know I'm going to end at 25 degrees Celsius, which is down there in that liquid region. And it's also telling me it's condensing, right? So I know that I have a phase change occurring at that first portion, that straight portion. That's going to be segment 1. And then segment 2 is going to be the temperature change from 100 degrees down to 25 degrees. So what I want to do is break this up so that way I can calculate not only the phase change, that condensation, but also the temperature drop from 100 degrees to 25 degrees. So we'll do the first one, the first segment first. So delta Q is going to be our mass, which is 100 grams. And I'm going to choose the delta H for condensation. So if I look at my values for what it could be, I'm going to choose the condensation one, which is negative 539. So altogether, this comes out to be negative 53,900 calories. So I've lost almost 54,000 calories here. On the other segment, I have a temperature change. So I'm going to take my final temperature, 25, minus my initial temperature, 100. And it's in the liquid phase, so let's not forget that. And that's going to be negative 75. So it's lost heat here. We've lost temperature, so it's going to be a negative number. My mass is still 100 grams. My temperature change is negative 75. And the C value I'm going to choose is going to be 1.0 because it's a liquid. So I'm going to choose the specific heat for water. So altogether, this comes out to negative 7,500 calories. So when I want to add up my Q total, which is how much total energy happened after both of these things occurred, it's going to be negative 61,400 calories. So at this point, you should be able to differentiate between the kinetic energy equation and the potential energy equation, and when do we use those. So the kinetic energy, again, for those slanted portions of the graph, potential energy for the straight portions. And then how do we do these multi-step problems where we have multiple steps occurring, and how can we use that heating or cooling curve to help us solve it?